is the Gar's Dilemma, efficient code reuse attacks against Intel SGX. And it is joint work between University of Padua, University of Duisburg-Essen, and TU Darmstadt. So I guess most of you know about Intel SGX. It's an extension to the x86 instruction set that allows applications to create isolated memory areas known as enclaves, which are not accessible to the rest of the system. The way it typically goes is applications can then interact with those enclaves by entering the trusted execution mode. The enclave is going to do some computation, and then it's going to exit back to the application with a result. All memory of an enclave is encrypted at the hardware level before being stored into physical memory. And an important feature of enclave is that they can perform remote attestation with a server. So they can prove to a remote server that they are running securely on a genuine Intel platform and they have not been tampered with. The SGX threat model has very, very strong attackers. So if an application is malicious, that's not a problem, can't read the enclave memory. If the kernel of the hypervisor is malicious, same thing, can't read the memory. If we have a physical attacker, even a physical attacker cannot read the enclave memory because it is encrypted even on the bus, on the actual physical board. However, interacting with the raw CPU instructions for SGX is pretty complex. So Intel developed an SGX SDK for enclave developers to make writing code easier. So it is clear now that SGX provides extremely strong isolation thanks to its unhackable security properties. Yeah, that's not how it goes. So latest attack was Foreshadow. It was presented here yesterday. And it's an attack based on meltdown that can read the whole enclave memory, completely break the security model, but we have had a bunch of side channel on SGX for years. Now, this is not the kind of attack that I'm going to talk about today. I'm going to talk about something a little less exotic, but SGX code is just normal code, actually. It just runs inside of an enclave, and it can have bugs. Especially we're interested in memory corruption errors. So if we have a memory corruption error inside of the enclave, what are the consequences? What can we do? And how can we mitigate against that? So I will give a very quick background on control flow attacks so that we're all on the same page. We have mainly two categories of control flow attacks. The first one is code injection, where the attacker injects some code into memory. This is typically called shellcode. And then by using a memory error, diverse execution, that's control flow hijacking, to that malicious code. To mitigate against this, we can use mitigations such as write XOR execute that stop code injection and also code replacement. The other category of control flow attacks is code reuse, for example, return-oriented programming. And in code reuse, instead of trying to inject new code, we reuse code that's already in the application. But we choose some small parts of the application called gadgets, and we use techniques such as ROP to chain together those gadgets. So for example, ROP chains together small sequences of instructions that end in a return instruction through the stack. So you have one gadget returning to the next one on the chain. To mitigate against this, we can use control flow integrity. And control flow integrity at compile time computes the possible valid control flow transfers in the program, and then checks those at runtime. So let's look a bit at the related work on memory corruption on SGX. On the attack side, we have dark ROP. When you want to do ROP on a program, you need access to the program binary because you have to analyze it and figure out where the gadgets are and what gadgets you have. With SGX, it is possible to create enclaves that are not possible to reverse engineer because you can encrypt the enclave, wrap it into a loader, and have a remote server after remote attestation give you the key. And the decryption happens inside of SGX memory, and you cannot access that. But dark ROP showed that it is actually possible to find gadgets, even if you don't have the code, by exploiting certain oracles based on the behavior of the enclave when it crashes. On the defense side, we have SGX-Shield. And SGX-Shield is a very strong hardening for SGX enclave, which first of all, performs fine-grained randomization. So it breaks up the enclave in very small chunks and randomly permutates those chunks at loading time so that the attacker does not know where things are. So even if the attacker has access to the binary, it doesn't know the addresses of the gadgets. It also employs a bunch of other mitigations such as WXRX, control flow integrity. The other piece of background that I need to explain our attack is the SGX SDK, because our attack is an attack on the SDK. So when you compile something with the SGK, the enclave code goes into the enclave binary, application code goes into the application binary. But you also have certain libraries that are inserted by the SDK. And in particular, we focus on two of them: the trusted runtime system, or TRTS, which runs inside of the enclave, and the untrusted runtime system, or URTS, which runs outside. And those take care of entering and exiting the enclave and abstracting all those low-level details about that and about passing data between the boundary between the enclave and the application. The SDK also allows applications to call functions inside of the enclave, and those are called ecalls. And we can also go the other way around and from the enclave call functions in the untrusted world, and those are called ocalls. Moreover, another important feature is that the SDK allows for exception handling inside of the enclave. So when an exception happens, you basically get an interrupt to the kernel. The enclave is stopped and the kernel gets the interrupt. But you want to handle that exception inside of the enclave to protect the enclave secrets. So what happens is that the kernel delivers a signal to the application, and then the URTS and TRTS work together to dispatch that exception inside of the enclave. And then it is handled. So now I can finally explain what our attack is. So first of all, it's a novel code reuse attack on SGX. So just a new way to combine gadgets into a chain. It reuses ROP gadgets, so we do not define a new kind of gadget. We use a gadget class that's already there. There's tooling to find it. But the most important thing is that it only uses the existing TRTS functionality to achieve this. Now, why would we want to do code reuse with existing TRTS functionality? The reason is, first of all, the SDK is widespread. So if we build an attack that is based on the SDK, it's going to apply to a lot of enclaves. Second, it makes exploitation easier, as we are going to see, instead of chaining small gadgets, we can actually go and chain whole functions, and it makes writing exploits really easier for the attacker. But the most important thing, I think, is that existing hardening does not cover the TRTS. So for example, SGX-Shield does not consider the TRTS, and this means that we can bypass it thanks to our attack. So what's the basic idea behind it? Say that we have a function, it has some memory corruption error, and we can exploit it, we can do control flow hijacking, we can write directed program execution. Inside of the TRTS, there are certain functions, we're going to look at them in more detail later, that restore state. So they're using, for example, in exception handling, OCall, they basically can set the whole CPU state. So what an attacker can do pretty easily is use that control flow hijacking to call those state restoration function, pass in a whole counterfeit state. And now the attacker has control over the whole context of the CPU. Now, you could do this with normal ROP, but it's more complex, and it might not bypass mitigations such as SGX-Shield. When you have control of the CPU state, you can then use this to further chain other, for example, function invocations. So we build our attack around two primitives. The first one, we call it the ORAT primitive. So this comes from the OCall mechanism, so calls from the enclave to the outside world. When you make an OCall, the TRTS saves the current execution context into the stack, the enclave stack, in a so-called OCall frame. Then it exits the enclave, and the URTS calls the untrusted function. When the untrusted function is done, the URTS re-enters the enclave, and the TRTS restores the previously saved context, so that we get back to the call side that invoked that OCall, and we can go on with execution of the enclave. From an attacker point of view, what you can do is you can create a fake OCall frame, so a fake context for an OCall, and then you can do control flow hijacking in that context restoration function. It's called do ORAT. That's where the name of the primitive comes from. And you get a partial control of the context. So you don't control the whole context, but you control just enough to do what we have to do. However, to do this, you need to be able to control the contents of the stack, because do already takes the context from the stack. But we're going to see that that is actually possible. The other primitive that we have, we call it the continue primitive. And in the continue primitive, the continue primitives comes from the exception handling mechanism of the SDK. So it's really similar to the override primitive. When an exception happens, you exit to the OS. Then there's a little dance where you re-enter the enclave and exit again and enter it again. It doesn't matter right now. If you want all the details, please see the paper. But what happens in the end is that the exception context is saved. So then when we get back into the enclave, the TRTS takes over and calls the exception handlers. And if the exception handlers determine that we can resume from that exception, then the TRTS restores the saved state. And we can abuse this in very much the same way as we did with the ORET. So attacker creates a fake exception context, and then control flow hijacking into that continue execution that restores the context. This time with this primitive, we get full control of the CPU state. However, the attacker needs to be able to control one CPU register before, which is the register for the first argument. So we have those two primitives, and they do slightly different things with slightly different prerequisites, but we can combine them, actually. So we call this an ORET plus continue loop. Take the ORET primitive. You need control over the instruction pointer, so that's control flow hijacking, and you need control over the stack. And when you have that, you can control the instruction pointer again, and you can control some registers. And one of those registers is RDI, which is the first argument register. The continue primitive needs, again, control of the instruction pointer and control over the first argument, and gives you control over the whole CPU context, including the instruction pointer and the stack. So what we can do is we can actually combine those. If we start from ORET, we can trigger the continue primitive. And if we start from the continue primitive, we can trigger an ORET primitive. Now, this is not very interesting on its own, you're just looping. However, on the your left-hand side of that drawing, we have controlled stack coming from the continue execution primitive. And if we have control stack, we can use that to launch a ROP gadget. Now, we don't necessarily, it doesn't necessarily have to be a small ROP gadget, it can be a whole function. So instead of chaining small gadgets, we can chain whole functions, because the continue primitive gives us complete control over the context, and we can set all the arguments and everything we want. Then that ROP gadget, since we control the stack, is going to return, and we can make it return to the ORET and kickstart the loop again. So let's have a look over the attack at a high level. First off, we prepare, we find the gadget, we design a chain, then we prepare a bunch of fake structures. This is a little bit time-consuming the first time the attacker does it, but then it's basically the same for all attacks. When we have those structures, we launch our attack. So in this example, I'm launching it from the continue primitive, but you can also launch from ORET. It doesn't really matter. It's a loop anyway. So we launch the continue primitive, and that continue primitive is going to restore a context from a fake exception info that was set up by the attacker. That's going to transfer control to gadget 1. Gadget 1, then it is going to execute and return through the stack that we had set up with a continue primitive, and it's going to return to the ORET. And with the ORET, we set up a call to the continue primitive again and go ahead with a loop. So let's look at an example of how you can use this. There's a vulnerable function, and then we have some other functions in the enclave. For example, a get key, which gets us some secret cryptographic key in the enclave, and a send file function, which can send a file to the attacker, for example. In the TRTS, we have ORET, we have continue. So we exploit that vulnerability. We get control for, in this case, for example, we get control of the instruction pointer and the stack. So let's say this is, for example, a stack overflow. Using that, we trigger ORET. From ORET, we can trigger continue. We have full control, and now we can just make arbitrary function calls, for example, to get key. which gets some key, writes it to some place in memory, for example, the stack. Now we can make get key return to ORET and do the same trick all over again, reset the whole context, call send file, and send that key over to the attacker. Now, how do we apply this to SGX-Shield? So SGX-Shield is based on the SGX SDK. So when you compile something with SGX-Shield, the enclave code gets split up in a bunch of randomization units, but also you get the SDK libraries in the enclave memory space. At loading time, those randomization units are randomly permutated. So it's very fine-grained. However, the TRTS is not randomized. So how can we exploit this? Well, attacking SGX-Shield has a few challenges. The first one is the randomization. However, like we said, the TRTS is not randomized, and our code reuse is based on the TRTS. So we can beat the randomization by reusing non-randomized code. The other thing is we have control flow integrity in SGX-Shield, which could break our attack. However, we found some issues in the instrumentation of the return edges of SGX-Shield. For all the details, please see the paper. But the main takeaway is that ORET is actually possible on SGX-Shield. So we can use ORET to bootstrap the whole thing and achieve our attack. So plus there are some other mitigations on SGX-Shield. However, those are implemented in software and they are dependent on CFI. So once the CFI falls, the other mitigations fall. So how do we exploit SGX-Shield? Well, the first thing that we do is that we hijack a return edge. Like I said, the CFI for return edges is not properly instrumented. Then we actually use the ORET plus continue loop to write some shellcode to memory. So in SGX-Shield, you actually have some writable and executable memory. That's a limitation of SGX when you have to do code randomization, at least SGX version 1. And that's why WXRX is implemented in software. We jump to that shellcode, and then we have our shellcode just steal enclave keys and send them over to the attacker. And you could basically do anything, but stealing keys is probably one of the most interesting things that you can do to an SGX enclave. Now, as for mitigations, we can think about hardening the SDK itself, so making it harder to fake those structures. And we can do this by basically embedding secrets into the structure that the attacker does not know. You can directly embed the secret, or you could mangle, for example, pointer by XORing them with the secret. This is used in quite a few libraries. So, for example, GNU libc does that for some structures. Or we could do external hardening. And one idea could be, let's extend SGX-Shield, which is actually pretty good. Let's just extend it to also randomize the SDK code. And another idea would be to have stronger CFI. So the CFI in SGX-Shield is pretty coarse-grained. We could make it more fine-grained. Obviously, there are some performance issues there, but that's certainly something that we could look into. So what did we learn? SGX presents significant challenges when designing hardening schemes. First of all, the attacker is very strong, but the real takeaway, I think, is that the SDK can increase the enclave's attack surface. You're introducing more code in your trusted base. You have powerful primitives in it, and there is low-level code that is pretty much hidden from sight, and which comes from the TRTS. So concluding, we presented a new code reuse attack on Intel SGX. We use kind of hidden, forgotten code in the TRTS to bypass even state-of-the-art hardening. And this really underlines the need to consider the implication of using the SDK and extending that trusted computing base. Thank you for your attention, and I'm happy to take questions now.
We've got time for a few questions.
Hi, John Criswell from University of Rochester. Nice talk. So it looks to me that your attack is corrupting, save program state or manufacturing save program state. This is something that we dealt with in the operating system kernel in the secure virtual architecture line of work, so SVA, Coffee, and Virtual Ghost, and now Apparition as well. I'm a little bit confused by your proposed defenses, right? So it seems like what's happening here is that you have a slight problem with your CFI, and then perhaps you're not protecting the save program state with SFI, right? So is that correct, or am I missing something?
So there are a few issues there. So certainly the CFI is one of them. If we had stronger CFI,
so is the CFI incorrectly implemented? Because I don't think you need fine-grained CFI. You just need to make sure your instrumentation isn't jumped over.
The CFI in SGX-Shield has some issues with return edges. Yeah.
Okay.
So that makes it all possible.
Okay. All right. But then is the state actually protected with SFI or not?
No. So that is actually a good idea. Protecting the save state with SFI. Yeah. So there is a part of the state which is protected by SFI, which is the state that is saved by the hardware itself, but the state that is saved by the software, that's not protected with SFI.
Okay, yeah. So I think the lessons from SVA may be applicable here. I'd like to chat further on offline if that's all right. Thanks.
I have two questions. First of all, why do you need, or why is the randomization of the SDK in enclave required for the mitigation?
So basically, one of the things that we're exploiting here is that SGX-Shield basically does not take the SDK into consideration, and so that piece of code that we are reusing is not randomized. And so we can actually figure out where it is in memory, because the actual enclave code, it's all permutated. And
so is that correct to assume that all of the mitigations you're proposing require code secrecy?
Sorry?
All of the mitigations you're proposing require code secrecy?
No, they don't. They no, the oh, sorry, wrong.
Is there an assumption of code secrecy?
So you were referring to those, right? They do not require code secrecy.
I guess I just don't understand why you need randomization of the SDK code if there's no code
if you randomize it properly, the attacker cannot figure out where it is, so reusing it is pretty difficult.
Okay. Thanks.
All right, yeah, let's thank our speaker.